Today we're going to take a look at the beginning stages of how to graph rational functions. We're not actually going to graph them until tomorrow. So first of all, a reminder what a rational function is. A function whose rule can be written as a ratio or division of two polynomials. And the parent function of all rational functions is 1 over x. So I'm going to sketch a little graph of what that looks like for you. And what it is it's called a hyperbola, and it's two kind of separate-ish graphs. And it has what are called asymptotes, which means a line that a graph approaches but never crosses. So as you can see, for the parent function, the asymptotes are the x and the y-axis. As the x value increases, the graph gets closer and closer to the x-axis. Because if we have 1 over a million, it's really, really close to 0, for example. So how to find our asymptotes? To find a vertical asymptote, it occurs when the denominator is 0. So in our parent function, when x equals 0. Horizontal asymptote is a little bit more complicated. So let's say we have a rational function, and all this is on page 594. I know it's a little bit blurry, so it might be hard to read. It says let f of x equal p of x over q of x, where p and q are polynomial functions in standard form, not factored form, standard form, with no common factors, other than 1, of course. The graph of f has at most one horizontal asymptote. The way I remember this is by looking at the parent function. I know the degree of the numerator, so that's the second one here, is less than the degree of the denominator. So the horizontal asymptote is the x-axis, or y equals 0. So if that's not the case, if it's the other way around, there is no horizontal asymptote. And if the degrees are equal, the horizontal asymptote is y equals lead coefficient of p over lead coefficient of q. If none of that made sense, hopefully it will when we see a few examples with actual functions. And finally, graphs can also have a hole in them. So for example, if the numerator and denominator have a common factor, that would just be a hole instead of an asymptote. All right, so let's start figuring this out. Let's look at vertical asymptotes first. Remember, a vertical asymptote occurs when the denominator equals 0. So it's basically finding the domain restriction. So when this example says determine the domain, zeros, and vertical asymptote, once we find the domain, we have the vertical asymptote as well. So that'll save us a step. All right, as I mentioned, same process for both of those. So we're going to set our denominator equal to 0. So of course, x cannot equal 9. That is our domain restriction. A vertical line has an x equals equation. So this is our domain restriction. And then the vertical asymptote would be the line x equals 9. For the zeros, that is when the numerator equals 0. So we set 2x plus 1 equal to 0. So x equals negative 1/2, and this is the 0. So this is where it will cross the x-axis. Looking at b, let's repeat that process. Where does the denominator equal 0? X cannot equal 0 is our domain restriction. And then our vertical asymptote occurs when x equals 0, or the y-axis. 0, setting that numerator equal to 0. Adding 5 dividing by 2, we have x cubed equals 5/2. Taking the cube root, and that would be our 0. And of course, if we were actually graphing, we would get a decimal approximation in order to plot that on the x-axis. And finally, we've got x squared minus 1 cannot equal 0 for our domain restriction. We could factor that. It's a difference of squares. But if we add 1 and take the square root, remembering that when you take the square root, you get plus or minus, our domain restriction, which means we have two vertical asymptotes, x equals 1 and x equals negative 1. And finally, our 0, where 2x equals 0, so x equals 0 is where our graph would cross the x-axis.